Okay, this is the second and probably the last hour of Physics 1C for October 18th. And what we're going to be talking about now are called RC circuits. RC circuits are a circuit that contains a resistor and a capacitor and possibly other things, but that's what you mainly need. So you need to have a resistor connected to, we're going to do an RC series circuit here. So this is connected to a capacitor. If you remember, it's been a week or two, so capacitor is the two lines where they're equal to each other. And this is going to be connected up with a switch to an EMF source. I guess we're going to draw the EMF source like this, although it doesn't really matter. So we have some ideal EMF source here with the positive side of the battery here and the negative side here. And we are going to talk about the way in which the current and the charge on the capacitor work in a circuit like this. And just in general, I'll tell you where we're going with this. When I close the switch right here, what's going to happen is that the capacitor is going to start to charge up. But depending on how big the resistor is, the current isn't going to flow on very quickly. That is to say, the resistor is going to slow the effort of the current to put charge on the capacitor, which means it's going to take time for the capacitor to charge up. And that's pretty much what the circuit's going to be about. Is figuring out how long is it going to take for that capacitor to charge up. How does the current vary as a function of time in the circuit? So the question is going to be at t equal to 0, the switch is closed, completing the circuit. Okay, and our question is, can we find the current flowing through the circuit as a function of time? I'm going to label that as little tiny I of t. And can we also find the charge on the capacitor plate as a function of time? Okay, those are the two things that we're going to want to figure out here. Okay, and how long does it actually take to charge up the capacitor? That's the other question that we're going to answer. Until it's fully charged. I think it's probably helpful before we do some mathematics to actually look at what one of these circuits looks like, at least from a like if we hook one of these up, what's it going to actually look like? So let's try that out. So we got a switch. We need a battery. Let's set it up the same way I set up my battery in the picture. I think I put the big side on it, right? Yeah, okay. Well, they've really changed this. This is a new one. I haven't tried this one out before. Even the way that things rotate is kind of funny. Okay, we need some wires. We'll connect these up like that. Get another wire going like this. And I'll have a wire come across the top right here. A wire over here. A wire right here. And now all we need is a resistor and a capacitor. So let's put a resistor right here. Oh boy. Are there capacitors? Uh-oh. Does this one really not have capacitors? Wire, battery, light bulb, resistor, switch. Fuse, battery, light bulb, resistor. I did the wrong one. I'm so sorry. Huh. Did they change this? What's this one? They've definitely changed this. They've created a new one. It's just I thought they had capacitors. They used to, at least. We have to go to the AC circuit one. If I go to lab, is that the one that I want to pull up? Let's see. It looks like the same stuff, right? I don't see capacitor. The one I want then is going to be. Let's just check to make sure. No, there's nothing here. So, can I go back? What we want is the AC circuit construction kit, I guess, then. But I don't see it, so let's do here. Something's missing. Oh wait, is it this that I have to get rid of? I think that's what it was. I think it's one of the older ones, and as a result, There we go. There's more here now, right? There's a lot more. Okay. This should be fine. Either one of these will work. This one should work fine. All right, sorry. I thought I had the right one pulled up before class, but I didn't realize that they've changed the way you interact with this now. Okay, so we're gonna hook up a little little circuit here. Should open in a minute. Okay, so here we go. Battery, wire. I can understand why this isn't supported anymore because it can have some problems for sure. Some simulation issues for sure. All right, so there's our switch, there's our battery. Now we just need to have a resistor and a capacitor, and they connect those up. So let's connect them up here with wires, like that. And then we just need to have, here I'll go like this, and like this, back down to here, and then connect this up. Now nothing's gonna happen initially because we, oh, you know what else we're gonna do? We're also going to put a light bulb in here. We're also going to put a light bulb so you can visually see what's going on. The light bulb has resistance as well. And we can see what the resistance is if we want all these things. Okay, 0.1 farads. Okay, there's our voltage. I just want to show the voltage. There we go. So we've got a 9-volt battery with no internal resistance. We've got a 10 ohm resistor connected up to a 10 ohm light bulb, which means the total resistance is what? What would the total resistance here be? If it's 10 ohms and they're connected in series, what's the total resistance? Checking to see if anybody's there. 20. There you go. 10 plus 10, 20, right? Our capacitor has a capacitance of 0.1 farads. That's a very large capacitor. So now here's what we're going to do. We're going to close the circuit and we're going to see what happens. Now the prediction is that due to the fact that there's a resistor in the circuit, the capacitor is going to take a little more time to charge up than usual. So here we go. Closing this in 3, 2, 1. And there we go. It happened pretty fast. It happened pretty fast. But we can do some stuff to make it happen slower. So basically what happened was, let me open this up, let me reset it. If you'll notice, at the very beginning, the current starts to flow. It charges this up, but the current kind of slows down. And eventually the current stops. Because the capacitor acts as a short circuit, right? It's like a gap, so the current can't flow anymore. So basically, and if I open it, nothing's going to flow as well because there's an open circuit. So at first the current flows, the light bulb brightens up, and then it gets dimmer and dimmer and dimmer. Okay, a very short demo. If I did this in real life, it would be much slower. Now what I can do is I can change the capacitance. Now I want you all to predict for me. If I were to increase the capacitance, do you think it will take more time or less time to charge up? So I've now doubled the capacitance to 0.2 farads. Do you think it's going to take more time or less time to charge up if it's a bigger capacitor, leaving everything else the same? Should take more time. Okay, let's just check. So we've doubled it. Let's watch. It's hard to tell, but since it hasn't quite stopped until now, I think you all would agree that it took more time, right? And you can see the capacitor has more charge on it. All right. Now we could actually increase the capacitance if we wanted to by adding a bunch of capacitors in series, and that would probably really change it. I wonder if we do that real quick here. I wonder if it's as simple as just doing this. Oh, here, let's open the circuit. Let's reset dynamics, because you increase capacitance when you add it in parallel, right? So let's make sure they both have, the biggest they can be is 0.2. So let's make both of them 0.2. Okay, it's done. Now we'll show value, This should have a total capacitance of what? These two here. 4, right? 0.4, right? So again, it should be slower, so let's try it again. Yeah, it's still going. It's taking quite a while, right? All right, let's open this up again. Let's reset dynamics. Let's break this junction. Let's just stick with 1, just to keep things simple. And then just remove this probably. Remove. Okay, let's connect this back up. Now let's see what effect changing the resistance has, okay? I'm going to increase this to 100 ohms. All right. I'm going to increase this one. You know what? I'll tell you what. We'll also remove this for now. We'll just have the light bulb. So we're going to go from 20 ohms up to now 100 ohms, right? By increasing resistance, do you think that's going to make it take less time or more time for the charges to build up and fill up the plate? Should be more as well, right? Because if we increase resistance, that's going to slow the rate at which the current can flow into here, which means it's going to take longer. So let's try it. All right, closing it again. Yeah, look how much it slowed down. Not only is it taking longer, but the rate at which the current is flowing is now significantly smaller. Right? It takes way longer. So what we figured out is that increasing resistance and increasing capacitance has the effect of slowing down how long it takes for it to charge up, right? Okay. One other thing that we can show you with this is, let's say that we take our battery out of the circuit, okay? And now we discharge the capacitor. So we just looked at charging a capacitor, but let's look at what happens when we discharge the capacitor. So now I've got my capacitor here, I've got my light bulb right here, and now if I close the circuit, all of the negative charges can come around here and annihilate with the positive charges. So now this thing acts as basically like a power source now. It's a limited power source, but it is very slowly moving. Probably going to 100 ohms here was a little excessive because it's really slowed down quite a bit. But hopefully you all get the idea of what's happening here. The combination of a resistor and a capacitor makes it so that there's kind of a time element to your circuit. And these type of circuits are used in things that have variable speeds. So things like, as someone mentioned earlier, blenders, windshield wipers, things that have different speeds that they can rotate at are often made up of something like this that's producing a timing element. All right, so let's look at this from a theoretical perspective then. What we're going to do is we are going to use our loop rule, okay? And we're going to traverse around the circuit like this. Yes, Patrick. Yeah, exactly. We're gonna close the switch. Okay, so we're going to go ahead and close our switch right here. And again, we're saying that switch is closed at t equal to 0. I'm going to say when we close the switch, there's going to be a current flowing through our circuit here that I'm going to call I. So little I is going to represent the instantaneous current. So that current's going to flow across here. That means that this is going to have some charge at a moment in time that I call positive Q. This side is going to have a charge that I call negative Q. So little q is going to represent the instantaneous charge on the capacitor at a moment in time. Okay. And now what I want to do is I want to use the loop rule. Okay. And apply it to the circuit. We're going to start right here. So going from left to right, from the positive to the negative side, if I'm using a loop rule and I'm going around clockwise like this is my loop. What do I write down for the EMF here? Positive or negative E? Plus or minus right here. What do I put? Starting from here, we're going around the loop clockwise. That's positive, right? So we get positive E. And then we're going in the same direction as the current, so we get negative IR. And finally, we're also going to get, I'm just going to write this here as negative Q over C. To remind you, when you have a capacitor, the potential difference across the capacitor is equal to the charge on the capacitor divided by its capacitance. So the potential difference drop across that would be negative Q over C. Okay? And according to our loop rule, these should add to 0. Okay. Any questions? You can see how we're going from the positive side of the capacitor to the negative side of the capacitor, which is why this is negative. Because when we go from negative to positive, you get positive, right? So the rules for the capacitor are kind of the same as the rules for the battery would be. Okay. So there we go. And I'm going to mention some other things here. First of all, what is the maximum charge? How are we going to know when the capacitor is at maximum charge? What would the value of the maximum charge on the capacitor be in a circuit like this? What would that be? Well, E is units of volts. So it can't quite be E. Should be related to E, though. What's the voltage across the capacitor going to be once the current stops flowing in the circuit? What's the maximum voltage the capacitor could reach here? The maximum voltage would be equal to the EMF, right? So delta V max, in this case, is going to be equal to the EMF. This is for the capacitor. Okay. The delta V max would be equal to the EMF. So what would the maximum charge be then? C times E, that's right. Yep. Because according to this equation right here, if I take C times delta V, it gives me the charge, right? Okay. So that's going to be my maximum charge. What's the maximum current going to be? What's the maximum current going to be? E over R, that's right. You take voltage and we divide by resistance. That's Ohm's law, right? Voltage over resistance. E over R. So that's our maximum current. Okay, let's think about some other things. What is the charge on the capacitor going to be at time equal to 0? So I'm going to remind you that at t equal to 0 is when the switch is closed. So what is the charge on the capacitor going to be right when the switch is closed at time equal to 0? Do you need to go back to this? So here's our circuit, right? Let's hook the battery back up to it. That's pretty funny. Look at that. All right. Okay. So let's start this over again. Let's change the resistance back down to 10 or something so it's not so slow. All right. So here's our circuit, right? This is exactly the same as the circuit we're looking at, okay? Reset dynamics. So this is time equal to 0. I haven't closed it yet. What's the charge on the capacitor right now? It's 0, right? I closed this, so right at the moment when I close it, it wasn't charged and now it's fully charged, right? But the idea is that at t equal to 0, there is no charge, right? The charge builds up after I close it, but it has to start from somewhere. It's going to start from 0, okay? Does that make sense to everyone? So what's the charge at time equal to 0 then? It's 0 coulombs. There's no charge on the capacitor at time equal to 0. What about the current in the circuit? What's the current in the circuit going to be at t equal to 0? What's the current flowing through the circuit going to be right when I close the switch? It's not 0. Look. This part you can kind of see. I don't know if it's super easy to see, but we can definitely see it if I throw in a current chart. Let's do that. Let's throw in a current chart. Now, there's no current flowing right now because the switch is open, right? When I close the switch, all I'm going to really have is an EMF, a resistor, and then this capacitor that wants to basically stop the current from flowing. But as long as there's no charge on the capacitor to begin with, it can't actually resist the flow of current yet. if you'll notice what happens here, watch what happens to the current. I don't know if this is going to be, let's see, what's the value of this? 9 divided by... okay, so this should work, but I think I can zoom in to here, and it should work just fine. Okay, so watch this right here when I close the switch, okay? So I'm closing it in 3, 2, 1. You see what happened there? After some time has elapsed, there's no current flowing. Why not? Because there's a capacitor, and it has a gap between it. The current can't flow between those two nodes. So after enough time has passed, notice that the polarity of the capacitor is now the same as the polarity of the battery. And the EMF of the capacitor is the same as the EMF of the battery, right? So the voltage here is 9 volts. And if I were to come in here and take a voltmeter out and look at the voltage of my capacitor right here, I'd find that it's also 9 volts, right? So the capacitor and the battery are basically fighting against each other, where it's like a tug of war, more like people pushing on each other. The battery's pushing this way, but the capacitor's pushing back this way. So it's like equal and opposite force leads to no velocity, no movement of charges, right? But let's open it back up and let's reset dynamics. Watch what happens. You can watch this now if you want to as well. But watch what happens to the current right when I close the switch. It spikes really high, and then it starts to fall off. Why is it falling off? Because eventually this thing's fully charged, and you can no longer put charges on it. That's right, so you figured it out, Kyan. That's exactly right. The current at time equal to 0 is when you have maximum current. Exactly. And we saw that maximum current was E over R, right? So this is I max. And that's equal to E over R. And the main reason why is because that spring, it can only... I'll just show you again. That capacitor right there, it kind of acts like a spring. And once it's fully charged, that's like a spring that's been fully compressed, and you can't compress it anymore. It acts as like a stopping point for the charge. The flow of charge can't flow anymore. And once it's fully charged, the current will drop completely to 0. This is definitely a better way to visualize what's happening here, because you can see it's kind of exponentially approaching this value. And eventually it'll reach 9 volts. Okay, so we've come up with an understanding of what we think is going to happen. We believe the maximum charge on our capacitor is C times E. We believe the maximum current flowing through our resistor is going to be E over R. We know that at time equal to 0, the capacitor is uncharged. And we know that at time equal to 0, the current should be maximum. So all we need to do is we need to solve for these values of the functions, and then we hope that this stuff bears out to be true as we're doing it. Okay, specifically those two conditions right here. We can make a couple other conditions here. What should Q be at time equal to infinity? If we let time go on to infinity, the capacitor will eventually become fully charged, right? And if we let time go on to infinity, what happens to the current? Current becomes 0, okay? So we have to satisfy all of these points. Our equation has to be that Q of 0 is 0, I of 0 is I max, Q of infinity has to be Q max, and I of infinity has to be 0, okay? This is what we have to get out of our equations once we've completely solved them, okay? So we'll check that once we get to the end. All right, now let's start solving this equation. The first thing that we're going to do is we're going to say, we know that the instantaneous current flowing in our circuit is directly related to the charge buildup on the capacitor. So we can replace current in our equation right here with dq dt. So let's do that. So we're going to have E minus dq dt. And you know what? We're also going to divide through by R. You know what? Let's not skip steps, because this is hard enough as it is. So it's that and that equals 0. So all I did was replace I with dq dt. Now let's divide through by R. Okay, let's divide through by R. So we'll have E over R. Hey, E over R, that's max current, right? Minus dq dt minus Q over RC is equal to 0. Now what I want to do is I want to get this dq dt kind of by itself over here on the right-hand side. So let's do that. We're going to have e over r minus q over rc is equal to dq dt. Now what I'm going to do is I'm going to multiply by c over c right here, so I can get a common denominator of rc. So I'm going to have ce minus q over r times c is equal to dq dt. Okay, so those of you that have taken enough math, has this come up in this class yet? I don't know. If you're taking my 1B class, which I know at least one person is, then this has come up in 1B. How do I want to solve this equation? My equation has a q in it. Our goal is to find what q is as a function of time, and I've also got dq dt in here. So what kind of equation is this? What kind of equation is this? It's a first-order differential equation, right? So this is a differential equation, and you say first order because the derivative is the first derivative, right? It's like f prime. Do you have any recommendations, those of you that know how to do this, of what the best way to solve this is? Or like a simple way to solve it is? You can just cue your mic and say it. Stuff like this is often easier to say than type. Separate variables. That's the right answer. So this happens to be what we call a separable. At least this is what I learned. We call it a separable differential equation because what we can do is I can multiply the dt to the left-hand side and I can divide this thing, which has a q in it, to the right-hand side so that it becomes dt over rc on the left-hand side. And on the right-hand side, we get dq over ce minus q. And now what we can do is we can integrate both sides. Because I have all my q's over here with the dq's. There's no t's in the equation, but if there were, I would have put all the t's over here on the left. And we're just going to integrate from time equal to 0, which is when we started, up to some time that I'm going to call t prime, some arbitrary time in the future. And on the right-hand side, we'll integrate from 0, and now it's q. So we're going to integrate up to some value of q prime in the future. Okay, so q and t are just kind of dummy variables because ultimately we want to get q as a function of t, and I don't want to make my variable of integration here be the same as my limits, you know. So that's just a way of doing that. Okay, everyone following along? Anyone have any questions so far? From here on out, it's just going to be math. So we did all the physics right there. And now we're just doing a bunch of math. So, anyone have any questions? I don't think so. Justin? No, probably not. I don't really think you have that many problems at all where you have to do this. I've definitely given exam problems where you had to do this though, so you need to pay attention to the method at least. Because this is like the easiest version of differential equations you can have. So understanding this method is important. It also just comes up in physics a lot. This particular method comes up in physics a bunch. All right, so let's get to solving this. So what's the integral of the left-hand side going to be? Well, resistance and capacitance, those don't depend on time. We can pull those out of the equation. So this equation is very simple. It is just going to be t, or let's keep it in green. It's going to be t over rc, evaluated between those limits from 0 to t prime. Okay, equals The right-hand side of this equation, I don't know if you all would prefer that we do a u sub. I'm not going to do a u sub, but it's just a constant, right? So what's the integral of this going to be equal to? No, Justin, you won't be expected to know that kind of stuff. Negative log of CE minus Q. Let's try that. So negative natural log of CE minus Q. Okay, let's check to make sure that that's going to work for us. So if I take the derivative of this, so if I do ddq of negative natural log of CE minus Q, what do I get? Well, the derivative of natural log is 1 over CE minus Q, right? God, that looks awful. 1 over CE minus Q. And then you have to multiply by the derivative of the inside, so you have to multiply by -1. So you end up getting 1 over CE minus Q. So it works. That's correct. The integral of this is going to be negative natural log of CE minus Q. If you prefer to use a u sub, you can. Plug in a u sub for this. It's going to save you like one step, I guess. Or it's going to add one step, but nonetheless, it'll work. So that's what we get. Now what I'm going to do is we're going to evaluate the limits. So on the left-hand side, it's just going to become t prime over rc. On the right-hand side, we're going to have negative natural log of CE minus Q prime minus the negative natural log of CE minus 0. So that's going to be equal to, we can take the natural log of a difference and we can write it as a quotient. So in this case, I really wish I'd multiplied the negative sign to the other side. I think I'm going to do that actually. Here, let's go back to this line right here. And let's just go ahead and shove the negative sign over here. Hopefully that's not too confusing. I want to leave it there. We're going to move it here, which means this is just going to be the natural log of CE minus Q prime minus the natural log of CE minus 0. I just moved the negative sign over there. Because then we can write this as the natural log of the ratio CE minus Q prime divided by CE. And that should be equal to negative t prime over RC. All right, I'm going to, jeez, I didn't do this very well. I want to shift this down some. So there's room between these things. So to do that, I need to do that, and then we'll just kind of shift it back up a little bit. I'll try not to write such slanted angles, but it's kind of hard not to. Next thing we want to do is we want to get the Q prime and the T prime out of here. I'm also going to say at this point, we no longer need to call them T prime and Q prime anymore. We're just going to call them Q and T, so I'm going to drop the primes. They were just kind of dummy primes after all. So now we just are going to raise both sides to the e power. So on the left-hand side, we'll have e to the negative t over rc is equal to, on the right-hand side, the e will eliminate the log here. So we'll have CE minus Q divided by CE. Multiply the CE to the left-hand side, so we'll get CE e to the negative t over RC is equal to CE minus Q. And now we'll just add the Q and subtract this piece to the right-hand side. So the Q is going to come over here, and we're going to get Q is equal to CE, that's that term, minus this thing. Okay, kind of a long derivation here. But the result is pretty simple. We're pretty much there. Now what we can do is we can factor out the CE from both terms. Okay, and now we've actually got our answer. Q of t, the charge on the capacitor as a function of time, is equal to C times E, which we said from before was that C times E was equal to Q max, right? So I'm just going to write it like this. Q max multiplied by 1 minus e to the negative t over rc. This is the charge on the capacitor as a function of time, which we can now plot, okay, on a graph. If I want to plot the charge as a function of time, then what it's going to look like is it's going to start off at 0, and it is going to asymptotically approach a line right here where Q is equal to Q max. Okay, that's what the charge as a function of time is going to look like. It charges up very quickly at first, and then the rate at which it's charging slows down significantly as it tries to reach maximum charge. According to the mathematics, it never truly reaches maximum charge. In reality, when you measure things, your measurement device is not going to have infinite precision. Now, we can see that on this here, if I open this back up, and I reset dynamics, and now if you just focus on this right here, right? Focus on this thing right here. When I close this, it charges up super fast. It's already at 5, 6, 7, but you can tell that it's slowing down, right? Now it's 8.7, 8.8, 8.9. It's really slowed down, right? It's really slowing down. And when it gets to here, it'll sit at 8.999 for quite a while before it ever ticks over to 9. And the same thing happens in the lab, and I can show you if you want when we go back to school. Okay, so there's our equation. Should box that in. That's our final result. And yeah. So there we go. That is the equation for the charge on a capacitor for charging a capacitor. And there's some interesting things that we can take out of this. The first thing that we can take away from this is if we look at R times C and see that it shows up in this exponential right here, we're going to define tau to be equal to R times C. This is called the RC time constant. And the way that it works is it gives you an estimate of how long it's going to take for your system to charge up. All right? Let me show you how that works. So we can rewrite our equation using tau as Q of t is equal to Q max times 1 minus e to the negative t over tau. Okay? Now, if we calculate what Q at 1 tau is equal to, at time equal to 1 tau, what do we get? We get Q max times 1 minus e to the negative 1, right? If I put t equal to 1 tau, then I'll get e to the negative 1, right? What's that equal to? Can you put this in your calculator for me and tell me what you get? What do you get if you plug in 1 minus e to the negative 1 in your calculator? What do you get? So you get 0.632. So what that tells you is that after one time constant, you've reached 63% of the maximum charge. That's what that says, right? 63% of the maximum charge. So where would that show up on our graph right here? Well, that would be somewhere like right around here. We would say at this point, right? If we call this t equal to tau right here, the time constant, then at this point, you would be at about 63% of your maximum charge. Right there, at 1 tau. What do you get for 2 tau? If you do Q of 2 tau, right, that's going to be Q max times 1 minus e to the negative 2. What's that one going to be? What's e to the negative 2? 1 minus e to the negative 2. This one I don't know. This is 86%. So this one's going to be Q max times 0.86, so that'd be 86%. If you do Q of 3 tau, you're going to have 1 minus e to the negative 3. So if we do that, you get 95%. So this is going to be 0.95 Q max. I'm going to go to 5, so we're going to do Q of 4, we're going to do Q of 5. By 5, I think you'll be at over 99%, or close to 99%. So if we do 1 minus e to the negative 4, and then 1 minus e to the negative 5. So I got 0.98 for this one, and 0.993 for this one. So you can see that after about 5 time constants, you should already be at 99% of your maximum charge, right? So let's pick some values. So suppose your resistor was something like the M series resistors that we used in the lab last time. Let's say you got a 1500 ohm resistor, okay? And let's say you connect it up to a reasonably large capacitor. So let's say you have like a 60 microfarad capacitor. That's a pretty big capacitor. What would R times C be? Well, you take 1500 and you'd multiply by 60 times 10 to the negative 6. R times C, and you end up getting a time constant of 0.09 seconds, or about 90 milliseconds. That would be the time constant if you hooked up a 1500 ohm resistor to a 60 microfarad battery. The time constant would be 90 milliseconds. So that means after 5 of these, which would be, let's call it 0.1, after about half of a second, this capacitor would be fully charged. After about half of a second. And then, of course, you could use that fully charged capacitor to be released to do something else for you somewhere in your system. All right, any questions about these ideas as we go through this? There's a few more things I want to say before we do a problem here. Let's check some things. First of all, we said that Q of 0 needed to be equal to 0. Let's see if that's true. If I plug t equal to 0 in here, what does this whole thing become? So Q of 0 would be Q max times 1 minus e to the 0, right? What's that equal to? It's 0, right? Because e to the 0, just to remind you, anything to the 0 is equal to 1. So this is equal to 0. That's good. That crosses off one of our boxes, so to speak, that we wanted to make. We wanted Q of 0 to be 0. So that's good. Our equation is correct to that. Sorry, I don't know why I made this purple. That was an accident. Okay, what else do we have to have? We had to have that as t goes to infinity, Q of infinity should also be equal to something. Let's see if we get that. So this is going to be 1 minus e to the, it's negative, right? So e to the negative infinity. And what's e to the negative infinity equal to? Or e to the negative very large number? It's 0, right? Because if you don't remember, e to the negative infinity, if you don't remember your negative power, it's just the same thing as 1 over e to the infinity. And e to the infinity is certainly on the order of infinity. And so 1 over infinity is usually called 0. So this is going to equal Q max. Again, this was one of the things we wanted to prove, right? That Q as time goes to infinity should be equal to Q max. And our equation works out for that. Now, what about the current? We haven't said anything about current yet, so let's talk about that. What we said at the beginning about current was that I could find the current if I just took the derivative of the charge on the capacitor as a function of time. So let's do that. If we take the derivative of this equation right here, the first term is going to be the derivative of Q max. What's the derivative of this term going to be? 0, right? So we have Q max. The derivative of negative e to the negative t over rc is going to be e to the t over rc, still negative. From the chain rule, we're also going to have to multiply by negative 1 over rc, so that'll cancel out with the negative sign, and we'll get Q max over rc is equal to this. But if we remember that Q max was equal to c times e, and we divide by rc, e to the negative t over rc, then the c's and the c's cancel, so we get e over r. But we also said that e over r was the same thing as I max, so normally the way that we would write this is that the current as a function of time is equal to the maximum current in your circuit multiplied by e to the negative t over RC. And I'll leave it to you to verify that I of 0 is equal to I max. That one's pretty easy. And that I, as time goes on to infinity, is equal to 0. Very easy to prove these, but I can promise you that that equation satisfies them. All right, so again, this is for charging a capacitor. This equation and that equation. These two are for charging a capacitor, when the capacitor starts at 0 and is charging up, okay? There's one other possibility, which is that you could be discharging a capacitor. And I will save you the time of being bored by me doing another derivation that's exactly the same, and instead I will just show you the results, which are that when you charge a capacitor, or sorry, when you discharge a capacitor, so what that's going to look like is you have a resistor, you have a capacitor, and you're connecting them where the capacitor starts off with its maximum charge, and you close the switch at t equal to 0. Given that, so that the capacitor is now going to act like a source, the result that you get is a little bit different, although not that much different. Now what you're going to find is that Q of t for the capacitor is going to look like this. It's going to be Q max e to the negative t over RC, and I of t, okay, I gotta look it up. I don't want to write this down incorrectly. This is the one that's going to be 1 minus. Yeah, Q of t is that, and I of t is I max times e to the negative t over RC. Negative sign. Yeah, I was like, there has to be a negative sign, right? Okay. All right. So let us do some problems. Do we have time? Yes, we do. Good. Probably just do these two problems and then we'll stop, because I don't think there'll be much time left over afterwards. All right, so let's grab our equation. We're going to want that. Okay, charging. Okay, before I move on, we just did a bunch of stuff. Does anyone have any questions about all this stuff? We started up here with an RC circuit. We derived the relationship. We found the time constant, R times C. Any questions before we start making some applications here? Alrighty. Well, charging a capacitor. So this says that we have a 10 mega ohm resistor is connected in series with a 1 microfarad capacitor and a battery with an EMF of 12 volts. Before the switch is closed at time equal to 0, the capacitor is uncharged. We want to find the time constant. What fraction of the final charge QF is on the capacitor at time equal to 46 seconds, and what fraction of the initial current is still flowing at t equal to 46 seconds. All right, so we have a resistor equal to 10 mega ohms. That's 10 times 10 to the 6th ohms. Connected to a battery with an EMF of 12 volts and a capacitor with a capacitance of 1 microfarad. That's 1 times 10 to the minus 6 farads. And in part A, they want us to calculate what is the time constant. As we said before, the time constant is resistance times capacitance. So you take 10 times 10 to the 6th ohms, and we multiply that times the capacitance of 1 times 10 to the minus 6 farads, and we get a time constant that is equal to 10 seconds. Pretty easy. We should probably check to make sure that these units make sense. So an ohm is a volt per amp, I believe. We can see that from the equation delta V is equal to I times R. The units of ohms are volts per amps. So the units of this would be a volt over an amp times a farad. We can get that from the equation that Q is equal to delta V times C. All right. Which means that farad is going to be coulombs per volts. So this is coulombs divided by volts, which means that this is going to cancel with this. And we know that if we have coulombs divided by amps, an amp is a coulomb per second. So this is in fact going to give us seconds, which is kind of cool that if you take resistance, the unit for resistance, and you multiply by the unit for capacitance, you happen to get time. It's quite interesting. All right. So that's part A. Any questions? All right. Part B says, what fraction of the final charge QF, which for me QF is Qmax, is on the capacitor at t equal to 46 seconds? What fraction of the final charge QF is on the capacitor at t equal to 46 seconds? How could we do that? Let tau equal to 4.6. Well, tau is kind of fixed. What do you mean exactly? Do you mean this exponent? Make the exponent 4.6?
No, I didn't realize tau was a fixed number, so I thought we could just kind of make it work in terms of what we figured it out to be and what we needed it to be from the problem.
Oh, okay, I see what you're saying. Yeah. Yeah. Okay. You're kind of on the right track because the exponent up here is actually going to be 4.6. So you are kind of thinking about it properly. Any other ideas? What do we want to do? We want to find the fraction of the final charge that's on the capacitor at t equal to 46 seconds. How could we do it? Using the equations that you see here. You've got all the equations you need right in front of you. Nope. Good guess. Not right, though. Yeah. Yeah, I think that's what we should do, Josh. And that's exactly right. I think we should just take our equation and plug in 46 seconds and just see what happens, okay? Let's see if we can figure it out from there. So Q at 46 seconds should be equal to Q max multiplied by 1 minus E. If we plug in 46 seconds, it'll be negative 46 divided by R times C, okay? But we already calculated that R times C was equal to 10 seconds, so I'm just going to divide by 10 seconds right here. All right, so we basically get that Q at 46 seconds is equal to Q max times 1 minus e to the negative 4.6, right? Now, what are we trying to solve for? What do we do next? It says, what fraction of the final charge? So QF is the same thing as Q max, by the way. I said that, but I will write it down in case it's unclear. Can anyone figure it out now? Just solve the parentheses. That's right, because I can write a ratio now that the charge at 46 seconds, right, divided by Q max is equal to 1 minus e to the negative 4.6. And so whatever this is equal to, that's going to give me the fraction that I want. That's the fraction that it's asking for, right? So if we plug that in, we're going to get 0.9899. Does that make sense to everyone? Anyone have any questions? Whew. No questions? All right. Part C says, what fraction of the initial current I naught is still flowing at t equal to 46 seconds? For this one, we need our current equation, which we said was this. Very similar type of equation we can do here. If we just put I at 46 seconds and divide by I max, that's going to be equal to e to the negative 4.6 again, which I'm pretty sure is going to be 1 minus this. So it's going to be like 0.0 something. So let's see what we get. Minus 1 times negative 1. So this is going to be 0.01, which is 1% of Imax. Does everyone understand? These problems really aren't that hard. They really aren't. It might seem hard right now, but that's just because it's new to you. When you actually sit down and work on this stuff, it's really not very challenging. All right, any questions before we move on to discharging a capacitor? All right, it says the resistor and capacitor of the example we just did. So let's put the numbers down again. Resistance equal to 10 times 10 to the 6th ohms. Capacitance equal to, what was it? 1 times 10 to the minus 6 farads. And now what we're given, it says the capacitor has an initial charge of 5 microcoulombs and is discharged by closing the switch at t equal to 0. At what time will the charge be equal to 0.5 microcoulombs? So we now know Q max is equal to 5 microcoulombs. And our circuit now is just a capacitor that starts off with positive Q max connected to a resistor and then we're going to throw a switch at t equal to 0. So we'll throw the switch at t equal to 0, right? So the only change here is that we have Q max equal to 5 microcoulombs, and now we know that Q as a function of time on our capacitor is going to be given by Q max multiplied by e to the negative t over RC. Okay. Okay. So, part A says, at what time will the charge be 0.5 microcoulombs? Can you all figure that out? Is that something you all can figure out? If I don't tell you how to do it, can you figure it out if I give you a few minutes? Give it a shot. Try to solve part A. At what time is Q on the capacitor equal to 0.5 microcoulombs? See if you can figure that out. I think that you have everything you need on the page. I'm going to give you 3 minutes. Everyone understand what you need to do? Oh, come on. Not a 3-second timer. That's so stupid. Plus. Do I just push plus? Is that what I do? 3, 0, 0. Play. Just don't touch it. Okay, that was 3 minutes. Is that enough time? Did anyone get an answer? If you got an answer, you can put it in the chat. 23, 23. Okay. Guess that's the answer, 23. All right, let's see if we can solve it. So, pretty easy to solve. So this is going to be Q of t. We don't know what t is. We're solving for t. So Q of t over Q max. Basically just want to get the t out of here, right? Is equal to e to the negative t over RC. We're going to have to put the log of both sides. If we take the log of both sides, we'll get the natural log of Q of t over Q max is equal to negative t over RC. We're solving for t, so if we do negative RC, natural log of Q of t over Q max, that should give us the value of t. Plugging everything in, it's negative 10 times 10 to the 6th ohms times c, which is 1 times 10 to the negative 6 farads times the natural log of, we want Q of t to be 0.5 microcoulombs, and we know that Q max was 5 microcoulombs. That's equal to t. We can actually just simplify this down and make it easier to do in the calculator. This is going to be negative 10 seconds multiplied by the natural log of 1 over 10. Is equal to t. So what's that? I assume that's what you all got. So if we do negative 10 times natural log of 0.1, you get 23. Good job. All right, to just do part B relatively quickly here. Part B says, what is the current at this time? We saw that the current as a function of time in the RC circuit, when it's decaying, is going to be equal to I max times e to the negative t over RC. So at 23 seconds, this is going to be equal to, so I max is e over r. E was 12 volts. So I max is going to be 12 volts divided by the resistance, which is 10 times 10 to the 6th ohms. To be clear what I'm doing here, I'm saying I max is equal to E over R, and E is equal to 10 volts. Not 10 volts, but 12 volts. Okay, so that E to the negative, and then we just put 23 seconds divided by RC, which we've seen already is 10. And so that gives us, let's see, E to the negative 2.3 times 12. And then we have to divide by this huge 10 times 10. Oh no, I gotta write it like this, 10e6. I got 1.2 times 10 to the minus 7. A very, very tiny amount of current. That would be equal to 0.12 microampere would be the value of the current at 23 seconds. And of course, we expect it to be relatively small because there's not much charge left on the capacitor. And the max value of the current is also quite small. So, isn't I negative? Yeah, I don't think it really matters, honestly. But yeah, I think you're right. There's a negative sign here, a negative sign here, and a negative sign here. But what is negative other than left or right? You know what I mean? It's not super important if you make it negative or make it positive, but you are correct. All right. I believe that's where we're going to stop today. I told you we'd stop a little early because we kind of skipped our breaks. I will say a couple things. One, just to remind you, we're doing a lab E-5 on Wednesday. It should be the first half of the class. I will also mention that your book talks about the way that circuit overlords, short circuits, and household wiring works. It's not something I'm going to cover in this class, but if you're interested in that topic of household wiring, I encourage you to kind of read the textbook if you find that interesting, but you don't have to. Anyway, that's all for today. Hope you all have a great afternoon, and I will see you in class on Wednesday for most of you. Take it easy.